Just a quick note or two on example 4. In example 4, they ask the question, when can we estimate sine x by the equation x minus x to the third divided by 3 factorial and expect an error no greater than 3 times 10 to the minus 4th. Well, first off, when you look at this, don't be flummoxed and say, well, where in the world did this come from? Obviously, where this comes from is the Taylor series, sine x, and hopefully you've worked through this often enough that this is familiar, minus x cubed over 3 factorial plus 5 x to the 5th over 5 factorial minus ... and on forever. But we're only going to need this term right here. So what this basically is just the first two terms of the Taylor polynomial. So when can we get away with this and have an accuracy at this level? Well, that's pretty easy to figure because we know that the absolute value of m here can be taken to be 1 because we're dealing with sines and cosines, so that the absolute value of our remainder is no greater than something like this, and that's equal to 5 times 4 times 3 times 2 times 1 is equal to 120. So we get something like this, and this has to be less than 3 times 10 to the minus 4th. Now, what's happening is here, the closer that x comes to 0, the smaller this number becomes, because this is a series that is centered at 0 and it's going to be most accurate at 0, okay? So in this particular case, the closer we are to 0, the better off. I think if you're confused by that, please look at figure 8.15. This is really a central point on Taylor polynomials and how they work. But anyway, when we look at this, then we could simply solve this equation, right? And we would come up with a value, and I think in the example it's something like 0.514. And so as long as the value of x is less than 0.514, then we can expect an accuracy at least as good as 3 times 10 to the minus 4th. So that takes advantage of how Taylor polynomials work and using the remainder and stuff like that.